I'm Anil Kumar, sharing with you one of the best questions to sketch using the techniques we have learned in calculus. The question before us is, sketch the graph of f of x equals to x to the power of 1 over 3 times x plus 3 to the power of 2 over 3. Now this is a radical function and we need to find its derivatives, analyze first and second derivative, and then sketch the graph. Let me share with you a test problem from the test paper itself from one of my students, and then we'll begin exploring this function in greater details. So the question before us in the test question is f of x equals to x to the power of 1 over 3 x minus 4 to the power of 2 over 3. So I've slightly changed this value just to give you a variation, right? So here is part of solution, and then there you are. The graph of the function looks like something like this, right? So since it is a radical function, you do expect such cusps and corners, correct? So that is a kind of graph for the function from the test paper, right? Now let us explore and figure out how to sketch graph of such a function. Now whenever you're given a function to sketch, it's a good idea to start with x-intercepts and y-intercepts. So if I write 0 for x, what do I get? So basically f of 0 is equals to 0, right? So that is our also x and y intercept, correct? So what we get here is that 0 is part of the function. Now do we have more x-intercepts? F of x is x to the power of 1 over 3, so at minus 3 also we have x-intercept. So we know that f of minus 3 is indeed equal to 0, right? So these are two zeros for our function. Now let us also look into the end behavior. When I say end behavior, I'm trying to say that what happens to the function if x value is very large. Let us say, or we can say, what is the limit when x approaches negative infinity? If I have a negatively large number here for the given function f of x, then negative will give me negative this place, but 2 over 3 will be positive. So the function actually approaches negative infinity. What happens for positive infinity? So that means end behavior. So as x approaches positive infinity, the function f of x, this will be positive, that will be positive, approaches positive infinity. That means the range of the function is from minus infinity to positive infinity. There are no restrictions on this function, and so we can write one thing, and that is about domain and range. So we have domain as x belongs to real numbers, and also range as y belongs to a real number. So there are no restrictions. We have two x-intercepts. These are the values, right? And now let us explore the other parts of the function. So what we have so far learned about this function is kind of like this. So let me sketch, or I'll make the sketch later. But we have x and y intercepts. Let us analyze the first derivative also. Okay. So first derivative for the function is f of x equals to x to the power of 1 over 3 x plus 3 to the power of 2 over 3. So let me write the first derivative here. We'll apply the product rule. Derivative of x to the power of 1 over 3 is 1 over 3 x to the power of that minus 1, that is minus 2 over 3, times x plus 3 to the power of 2 over 3 plus first function, which is x to the power of 1 over 3, times derivative of the second, which is 2 over 3 x plus 3 to the power of 2 over 3 minus 1, that is minus 1 over 3. Correct. Now this can be actually simplified. It looks very challenging to simplify. 1 over 3 is common. Let's take the number 1 over 3. x to the power of minus 2 over 3 is common. So we'll set x to the power of minus 2 over 3 and x plus 3 to the power of, which is lower, minus 1 over 3. So we'll take these common factors and then see what remains. So from this term, we have already taken 1 over 3. We have taken this. Now here, we have taken minus 1 over 3. If I add that, I get 1. So I get x plus 3 as a factor here. And in this place, we have 2 times. We'll write plus 2x here. And we have already taken that term. So we're left with this term. So we can now write this as x plus 2x is 3x and plus 3. So we can write kind of like this. We have 3 times x to the power of 2 over 3 and then x plus 3 to the power of 1 over 3. I'm taking that in the denominator. In the numerator, I have 3 times, because this is x plus 2x, 3x plus 3. So I'll write this as 3 times x plus 1. Do you see that? So that is how we could simplify the first derivative. Now 3 and 3 cancels. So we have x plus 1 divided by x to the power of 2 over 3 times x plus 3 to the power of 1 over 3. From here, we get some critical points, right? So we have critical number. Critical numbers for us are at x equals to minus 1 from the numerator. From denominator, 0 and minus 3. 0 and minus 3. So we'll analyze these critical numbers now. So to analyze the critical numbers, let me draw a number line. I'm squeezing in so much of information here since I know we have very limited space to work with, right? As always, but I think I'll give you all details to solve this question. This is extremely difficult and important. So minus 1, 0, minus 3. Let me write minus 3 here, minus 1 and 0. Between these critical numbers, we have interval. Minus infinity to minus 3, we say test point can be minus 4. Test point here could be minus 2, minus half, and we could take 1 as our test point. So these are the test points for us. Now let us see what happens to the derivative itself. So the derivative, that is the equation. If I substitute minus 4, then my numerator will be negative, right? So numerator is negative. Denominator, this one is always positive. So this is always positive. And here minus 4 will make this negative, right? So negative. Now that negative will make it positive, right? So what I will do here is I will write this as positive, right? This everything is equals to positive. So in this interval we get positive. That really means that the graph will be increasing. You get the idea, right? So the graph will be increasing. Similarly, we'll analyze the other one. Minus 2 means negative on the top. This is always positive, and this minus 2 will be positive. So that means negative for us, correct? Negative means it will be going downwards, the function, right? And what we analyze here is that this part is negative for us, correct? That one was positive. If I substitute minus half, then the numerator is positive and these two terms are also positive. All will result into positive increasing interval, and when I substitute 1, even then all will be positive, correct? So that is again increasing interval. Perfectly fine. But that gives us our local minimum and local maximum. So from here, that is the local maximum, right? So we have at minus 3, what do we have here? Local maximum. Do you see that? So at minus 3, we have local maximum, and at minus 1, we have local minimum. So this is local minimum, and this is at minus 1. So what we will do is we'll find the value of the function at minus 1 now. So if I substitute minus 1 here, I get what? I get minus 1 times minus 1 plus 3 to the power of 2 over 3, right? So that is equal to how much? Let me use the calculator and find the value. So minus 1 means negative, and here it is 2 to the power of 2 over 3. So 2 to the power of, okay, within brackets 2 divided by 3, bracket close, right? And this is equal to 1.58. Let me write this as 1.5, or let's say 1.6, okay. So we have local minimum of minus, I should have written here because that is minus, okay. So this is local minimum. So what we get here is local maximum at minus 3. That means the point is minus 30, and we get local maximum, minimum at minus 1, and the value is minus 1.6 for us. So we get this very important data. So let me highlight this. We'll use this later. Okay, so that is from the first derivative. We already know about the x and y intercepts, which are these, correct? Okay, now let us find the second derivative, and that's a very difficult part. Finding derivative of this, right? So we'll have second derivative of that rational kind of radical function. So that means square of the denominator. That's the easy part. In the numerator, what do we get? So let me write square of the denominator, x to the power of 4 over 3 times x plus 3 to the power of 2 over 3, right? Derivative of x plus 1 is just 1, so I'm writing this term here. I get x to the power of 2 over 3 times x plus 3 to the power of 1 over 3, right? So that is the first term minus. Second term is x plus 1 times derivative of this. We'll apply the product rule. So that gives us, let me put square brackets, 2 over 3 x to the power of minus 1 means x to the power of minus 1 over 3 times x plus 3 to the power of 1 over 3 plus, now we'll write x to the power of 2 over 3 times derivative of this, which is 1 over 3 times x plus 3 to the power of minus 2 over 3, right? Perfect. So that becomes the second derivative. Let us simplify this one. So simplify means, okay, denominator is 4 over 3 times x plus 3 to the power of 2 over 3. You can see here that we can take some x and x plus 3 common. Which is the lowest power? Minus 1 over 3 is the lowest. So we'll take x to the power of minus 1 over 3 and x plus 3 to the power of minus 2 over 3 as common. Okay. So we're left with, since we have taken 1 over 3, we're left with x here, and here we get times x plus 3 minus, we have x plus 1 within brackets. We have taken 1 over 3 common, so we're left with 2 over 3 here. Okay, let me write 2 over 3. As far as x plus 3 is concerned, we get minus 2 over 3 common, so we get x plus 3 here. Okay, plus, in this case, x 1 over 3, so we'll write, okay, x over 3. We have already taken that part common. So this is what we get, right? Now we can simplify it further. These two terms can be combined by the denominator. So let me write this as x to the power of 5, 1 plus 4, 5 over 3, and then x plus 3, 2 plus 2 is 4, 4 over 3, right? That goes in the denominator. Let's open this numerator part. So we have taken care of this. X square plus 3x. Let me write this as x square plus 3x. Now we have minus x plus 1 times. So 2 over 3 of x plus x over 3 is just x. So we get here. And 2 over 3 times 3 is 2. So that gives us 2, right? So that is 2. Now, let us now simplify the second derivative expression. So what we get here is x squared plus 3x minus, let me expand this, x squared minus 2x minus x minus 2, right, divided by x to the power of 5 over 3 times x plus 3 to the power of 4 over 3. Now the numerator, x squared minus x squared is 0. 3x minus 2x minus x is 0. You are left with minus 2 in the numerator divided by x to the power of 5 over 3 times x plus 3 to the power of 4 over 3. Now from here you can easily see that there are two critical points. One is at x equals to 0, the other one is at x equals to minus 3. So let us analyze these 2 points for the second derivative. So for second derivative, we'll analyze concavity on either side of these 2 points, which is 0, I should write minus 3 here, and 0 on this side. So let me take a test point on either side. From minus infinity to minus 3, minus 4 is a good point, minus 1 between minus 3 and 0, and 1 on this side. Now, if I substitute minus 4 here, we know numerator is negative, so let me write negative for the numerator. This x to the power of 5 over 3 will be negative, right? So it will be negative times this is 4 over 3, always positive, right? So that becomes positive here. So this is positive. Positive means it is concave up, correct? So positive means concave up. So this is this kind of a graph here. Now between minus 3 to 0, minus 1, numerator is negative. This will be negative for minus 1, so negative. And here we have positive, right? So it is positive. That means negative negative gives us positive, so that part also is going to be concave up. Now on either side of 0, if I substitute 1, numerator is negative. Denominator, this becomes positive, right? Positive 1 times positive 1. So we get negative here. Negative means concave down. Since the concavity changes at this point, we have point of inflection at 0, correct? So what we can say is that we have point of inflection at 0, right? So at 0. The value at 0 we know is 0. So that is the point of inflection. Now we can summarize all these things and put them on a graph. So let us kind of sketch them. So what we have here is that we have, if we analyze this, what we find that the x-intercepts are at 0 and at minus 3. So let us say this is at 0 and let this be minus 3 for us. These are my x-intercepts. Now the graph is concave up in these 2 intervals. So from minus infinity to minus 3 it is concave up. So we get a graph like this, and it is going to negative infinity. That is the end behavior, right? Which we found at this stage, correct? So end behavior we found here, that the limit of the function as x approaches negative infinity is negative infinity, positive infinity is positive infinity. Now it is a radical function, so we expect cusp, right? So that is the cusp at minus 3. Now on this side it has a minimum, local minimum at minus 1. So we could actually sketch it kind of like this, and at this point it's concave up. Now the concavity changes, so it's kind of like this here, right? So that is how the graph is going to be. Now we know at minus 1 the value of the function gives us the minimum. So the critical points we analyzed was here at minus 1 we have minus 1.6. So let us say this is minus 1, and that's the minimum at minus 1.6 approximately. We have point of inflection at the origin, right? So that is how the graph is going to be for the given function, and that indicates the end behavior. I hope that this helps you to understand all the concepts required to sketch a radical function. Let's summarize. Whenever you have a function to sketch, start with their x and y intercepts, look at the end behavior, define domain and range. First derivative will give you local minimum and maximum. We found local maximum at minus 3, minimum at minus 1. And then second derivative gives you concavity. From concavity, we know shape of the graph, right? So it's concave up, concave down. We also find point of inflection, which is at origin in this case. Once you have these points, you can easily sketch an accurate graph. I hope that really helps. Thank you and all the best.